All right, ladies and gentlemen, welcome back. We are going to be starting a new unit today on chemical equilibria. And just as a reminder, the quiz on problem set 1 goes until Wednesday, and your quiz from the lab program should have stopped last night from the first experiment. So the second experiment, experiment 2, is available for you to do the data collection Tuesday, Wednesday, and Thursday, and the report or those quizzes are going to be due next Monday as well. So that's the routine we're trying to get in the course. And like I said, we finished the kinetics unit. The problem set quiz on the kinetics unit is going to run this Saturday, Sunday, and Monday. So it will open up on Saturday and close on Monday. And again, it will be like before, where you have a window of 45 minutes to answer the questions anytime during that period. So, all right. So what we are doing here is we are going to be looking at chemical equilibria. And we're going to be spending quite a bit of time on chemical equilibria. So the next 12 classes or so are going to be spent on these 4 chapters. Principles of chemical equilibria is going to be the largest one because the concepts that we're going to learn in chapter 15 are going to be applied to acid-base equilibria, solubility equilibria, and complex ion equilibria. Chapter 7, the additional aspects, deals more with things like buffers and titration curves, more advanced concepts of acids and bases, because it's stuff that you're going to see in the laboratory experiments that you do. So that's kind of what we're going to be doing, and this is actually going to take us, like I said, for the next 3 weeks. 12 classes, next 4 weeks. Next 4 weeks we're going to be spent on this module. So what I'm going to do now is I'm just going to give you an overview of the next month of material, and then we're going to go back and we're going to start looking at this in a little bit, in a lot more detail. So this is an overview. I'm going to go through it quickly. All chemical systems ultimately proceed to the lowest energy state of the system. We haven't done thermodynamics yet, but when we do thermodynamics, we're going to find that to understand why a reaction occurs, it occurs because it wants to get to the lowest energy state. And equilibria is a part of thermodynamics. So that lowest energy state could be where at all of the reactants, where all the reactants are lower energy than the products, and so no reaction occurs. That's one possibility. Another possibility is the reaction could proceed to completion and everything has been converted into products. The third one, which is of course interest in this module, is that of equilibria, where the lowest energy state has both reactants and products present in some proportion. And that is the concept of equilibria. I mentioned that chemical equilibria is one aspect of thermodynamics, and the only thing that matters for equilibria is the difference in energy between the reactants and products. Kinetics determines the rate at which equilibrium is achieved. So, for example, we have this reaction here of iron plus oxygen going to form iron oxide, rust, it's rusting. The products are extremely favored. This reaction probably actually goes to completion to form all Fe2O3. But the barrier is so high that it doesn't happen spontaneously. It takes tens of thousands of years for equilibrium to be reached. And so we can have things like buildings made of iron, automobile blocks made of iron, and that type of idea. And as a matter of fact, as chemists, we can control the conditions such that the iron actually doesn't rust. We can produce stainless steels that do not oxidize by changing the chemical environment of the iron and making something that doesn't actually rust. So, as part of the overview, you have reactants in equilibrium with products. R is in equilibrium with P. From this, we can get an equilibrium constant, which is just simply products over reactants, and we'll be going into more detail on this in literally 5 minutes. The value of the equilibrium constant ranges from 0 to infinity. If the equilibrium constant is 0, we have a reaction that doesn't react. If the equilibrium constant is infinity, the reaction goes to completion. 1 is the midpoint in the equilibrium constant. Less than 1, the reactants are favored. Greater than 1, the products are favored. And equilibrium is ultimately affected by primary factors that affect the entities involved in the equilibrium. You're literally affecting the reactants and products directly. The secondary factors affect the chemical environment. The environment surrounding the equilibrium will have some effect on the equilibrium itself. You probably haven't seen anything about secondary factors yet. You have seen those primary factors when you have a discussion on Le Chatelier's principle. Le Chatelier's principle is another way of saying how are the primary factors affected in the equilibrium. How is the equilibrium affected therein? That's the overview. Now we're going to go into detail on chapter 15. These are the sections in chapter 15 that we are going to be covering. I believe it's the entire chapter. Much of this material was covered in high school chemistry. If this is something that might be a faded memory to you, I have placed a lot of resources listed on Blackboard that you can go to brush up on it. And there is a very good introductory book by Mark Bishop. It's an electronic book. It's free, that you can go and remind yourself about the basics of chemical equilibrium, of all the concepts that we're learning here. The textbook that we're using here at UNBC, the Chemistry by Petrucci, is a fairly high-level book, and it has an expectation of that you remember some stuff from high school. If, of course, if that's not the case, I highly recommend looking up some of the other resources that are available, Mark Bishop's book being one of them. So, within every chemical system, reactions are constantly occurring, okay? Equilibrium, it looks like nothing's occurring, but in reality, there are still reactions that are occurring. It is just that the reactions moving in the forward direction to produce products and the reactions moving in the reverse direction to regenerate your reactants are occurring with the same rate. So a chemical equilibrium exists when the forward and reverse rates are equal. And we just did kinetics, so we can express the forward rate and the reverse rate. The reactions have not stopped, but the reagent concentrations are unchanging in time. We're using up reactants at the exact same rate that we are regenerating them. So we look at its very core, we have two reactions that are occurring. Reactants going to form products, and products going to form reactants. So we can write the rate expression for the forward and reverse reactions. And I'm just going to flip over to the tablet and just finish off this page. So the material that I'm going to be doing now is what would be on that page. So this gives us a very simple equilibrium of reactants in equilibrium with products. And we can have a forward reaction and a reverse reaction, rate constants. And so when we are at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. And remember, rate would be equal to K times the concentration. This would be K forward times the reactants is equal to K, lowercase k, reverse times the products. That is the premise of equilibrium. The rates are equal. I can rearrange this to get K forward over K reverse is equal to P over R. And because the rate constants are exactly that, they're constants, a constant divided by a constant is just another constant. And we call that constant, capital K, the equilibrium constant. So what I've just done is literally derive the equilibrium constant from kinetics. So we derive the equilibrium constant from kinetics. Kinetics, equilibria, thermodynamics, electrochemistry, all interrelated. Because we did kinetics first, I've just shown the link between kinetics and equilibria by rederiving the equilibrium constant. The other thing that is important to remember is about the rate constant is that it is a function of temperature. So that means the equilibrium constant is itself a function of temperature. And honestly, that's just what was written on this page. The equilibrium constant is a function of temperature. So what is the equilibrium constant? It's the ratio of the forward to reverse rate constants. It is the ratio of products to reactants for a chemical system. I just used P and R to be very generic. I can still be generic by using A and B reactive forms C and D, or R in equilibrium with C and D. The equilibrium constant for that reaction is presented there with the products raised to their stoichiometric coefficient divided by the reactants raised to their stoichiometric coefficient. The one difference that you might see here is that we're raising things to their stoichiometric coefficients, not to some arbitrary power or order of reaction. It's a fairly high-level process to show that overall it will end up being the stoichiometric coefficients. For purposes, just take it from here. If you want to learn more about it, there's a graduate course that you can take on PhysChem that probably will go through and show that for an equilibrium system, it will always be the stoichiometric coefficients that it is raised to. In general, for kinetics, though, it doesn't need to be the stoichiometric coefficients if you're just measuring the rate of reaction. High-level nuance. So if we look at this and go back to what we remember about kinetics, we remember that we've got a catalyst. And this is what a catalyst does to the system. I'm asking you, how does a catalyst affect equilibria? I'm not going to put you in breakout rooms for this one. I would appreciate it if someone could just offer their thoughts on this. It's one question, and we'll go from there. How does a catalyst affect equilibria? David Atu says it doesn't. Dylan agrees with David. Are they right or wrong? Everyone else is sitting on the fence. Excellent, excellent, excellent.
Well, I think that if it's in equilibrium, then the catalyst would have an effect, or it would lean towards the products or reactions, depending on what it catalyzes.
You're right. Once you figure out how I teach, I will never be negative towards a student unless I am in the wrong. So you are correct. It doesn't affect the equilibrium constant. It absolutely doesn't affect the equilibrium constant. But as Cassidy pointed out just in the chat, it helps you reach equilibrium faster. By lowering that activation energy, you reach equilibrium faster. But the equilibrium concentrations of reactants to products is unchanged. So you're completely correct. going back to this, the one thing I didn't do is I didn't tell you the units of C and D. I didn't put brackets around C and D. The other way that you can report the amount of a substance is by pressure. I didn't tell you the pressure, that these were gases and I was reporting the pressure. Okay? I didn't give you the dimensionality in that expression because it is neither concentration nor pressure. The title of this slide is activity. That's what we're going to get to in a few seconds. Activity is actually the effective concentration of an entity. And to give you an analogy, something that you might have experienced living in Prince George or living rurally is the fact that sometimes people go missing and there needs to be a search party. So imagine 20 people gather together to search for a missing person or a missing group that is out in the woods. As a search leader, does the search leader send the 20 people in different directions? Does he send one down this path, one down that path, one to do whatever? Does he send them all out individually? The answer is no, he doesn't. For the safety of the searchers, he sends them out in groups of 2 or 3. So 3 people might be walking down a relatively rocky terrain, 2 people might be checking a couple of paths, and so that 20 person of searchers is broken up into probably 6 or 7 or 8 groups that are searching different areas. You can't search all of the trails quickly, but you are doing it for the safety of the searchers. The effective search capacity has been reduced from 20 down to, 7 or 8 or 9, because going down a path, they can see a little bit better, but it's reduced. That is the effective search capacity for that process. We have the same thing in chemistry, and it is the effective concentration. So carboxylic acids are known to dimerize. They form beautiful double hydrogen bonds to each other, and the carboxylic acids move through solution as a dimer. You don't have 2 independently floating carboxylic acids. You have them joined together and moving through solution together. The effective concentration of the dimer of the acid is reduced. That would be called the activity of the acid. So, a couple of terms, and then we're going to simplify this. Activity, given a scripty A symbol, is the effective concentration of an entity. The other one is fugacity. Fugacity is the effective pressure of a gaseous entity. Both activity and fugacity are calculated the same way. There is some activity coefficient or fugacity coefficient that is multiplied by what we would say this is what we expect is the concentration to be, this is the pressure. Going back to our search party analogy, okay, we have 20 searchers, so we have 20 is the true value, but the effective value is about 1/3 times 20, which is around 7. So the coefficient would be 1/3 in that regard. The activity coefficients are dimensionless. It's just how is this being reduced or increased, actually. It's possible for activities to be greater than 1. And so if the coefficients are dimensionless, then activity and fugacity have the same units as concentration and pressure, respectively. However, we're not going to spend a lot of time on activity or fugacity. As a matter of fact, we're actually going to use activity as the most general term. People, when they talk, it doesn't matter whether they're talking about gases or solutes in solution, it's simply activity. Then the term that's used is the symbol A. So we're just going to say we have to worry about the activity of the solute and not worry about the term fugacity. I just want to expose you to it. We should be using activity. All of science should use activity and not concentration or pressure in their calculations. However, we don't. We don't because the activity coefficients are very difficult to calculate. The activity coefficient is dependent on how much of a substance you have. It's dependent on the temperature. It's dependent on the solvent or the environment that it is in. And adding any other entity will affect the activity. The example that's presented in the graph here is the activity coefficient of a number of different ions: hydrogen, hydroxide, ammonia, calcium, carbonate. Just a selection of ions that have given you the activity in a salt water solution. So we're changing what's called the ionic strength, how much sodium chloride is present. Now, sodium doesn't react with any of those entities. Chloride doesn't react with any of those entities. However, what they do is they affect the activity coefficient. If you look at the inset, as we get to 0 ionic strength, a pure water solution, the activity coefficient approaches 1. So in the limit of infinite dilution, the activity coefficient is 1. But as soon as you start throwing other ions into the mixture, you end up seeing substantial deviations from 1. And that 1 is often called unity rather than 1. I don't want to explain it. So yes, so we end up having the activity coefficient differentiating. And it depends on the ion, depends on what happens. Carbonate goes low and stays low, the others go higher. And for example there, the hydrogen ion actually increases to have an activity greater than 2 at high ionic strength. None of this you need to remember other than the fact that it changes, and it changes markedly. And for hydrogen, it's also presented there over a 50-degree temperature differential to show that the activity coefficient is a function of temperature. Basically, it's really hard to calculate the activity coefficients, so we don't do that. For the majority of chemistry, we make the assumption that the activity coefficients are equal to 1 or equal to unity, and so the activity is equal to the concentration or pressure. That is the approximation that we are making. Now, the approximation is reasonably good for gases. It is okay for neutral entities in solution, but it is actually poor for ions in solution. And that's represented by this figure right here. Okay? The activity coefficient of the ions presented here differ very markedly from unity. Where do we care about this? We care about this when we're trying to do quantitative measurements. So if you continue on in chemistry and you take analytical chemistry, or you're going to be doing environmental science, you should be taking into account the activity because that affects your results. And as you can see from this figure, the activity coefficients range from about 0.1 for carbonate up to over 2 for the hydrogen ion in just that environment. They change dramatically, and so it does affect your results. However, what we are going to be doing in this class is assuming that the activity coefficients are 1, are unity, and that activity is equal to concentration and pressure. What you're going to see, I'm presenting this just to let you know that it exists, and that when you take other courses, you'll see the concept of activity brought forward again. But we're going to use activity in this course later because we need to explain some of our observations. Some things won't make sense in other units, or in Equilibria and in other units. And the reason why it doesn't make complete sense is because we're ignoring activity. Once we take activity into account, it all makes sense. And I will be bringing them to your attention so that you have an idea of what anomalies disappear if we actually do the calculations properly. All right, so does anyone have any questions on that before I move on to the equilibrium constants? I'll give you about 30 seconds to type in your questions or ask them through the chat, please. We're good? We're good. All right. Well, if we're good, we're going to continue then. And look at equilibrium constants. And probably going to be looking at equilibrium constants to a greater depth than what you had in high school. And while you may have seen this material, we're reviewing it and we're taking it to a greater depth, more advancing your knowledge. So the first one I want to look at is the thermodynamic equilibrium constant. The thermodynamic equilibrium constant retains the normal reporting state of the reagents. So for gases, we report gases in varying units: bar, pascals, kilopascals, atmosphere, millimeters of mercury. All of those are very common units for reporting gases. If you're dealing with solutes in solution, you're generally using moles per liter, but it wasn't always moles per liter. Does anyone remember what the unit that was more common historically was for concentration? Wasn't molarity, it was what? You can Google it if you wish. And not density, but Mark proposed molality, and that is correct. Molality was the historical common unit for concentration. It is moles of solute per kilogram solvent. Moles of solute per kilogram of solvent. That's molality, yeah, M-O-L-A-L. Yeah. Molality does have a lot of benefits over molarity in the sense that it is independent of temperature. While a solution might vary in volume as a function of temperature, the density changes, molality doesn't have that. We did move to molarity, but I want to caution you or point out that if you are looking up equilibrium constants, and there are books that list equilibrium constants, you will very likely, if it's a older equilibrium constant, it will probably be based on molality, not molarity. If you're working in aqueous solution, it's only a small error. But if you're working in any other solvent where the density isn't equal to 1, it becomes a fairly substantial error. It also becomes a substantial error if you have large amounts, higher concentrations of your solute, because that affects the mass in that regard. So there we have the old one. Molarity is common today, but just be aware that historically molality was common. The thermodynamic equilibrium constant can be, does have some special versions of it. If you have a solution that only contains gases, then you have the pressure equilibrium constant. If you have a system that only contains solutes, then you have concentration equilibrium constant given the symbol Kc. So what we're going to do now is we're going to write the thermodynamic equilibrium constants for the following. And then there are 5 listed there. So the first reaction or equilibrium that's present is that of SO2 plus 1/2 O2 as a gas is in equilibrium with SO3 as a gas. And so here it's simply products over reactants. would be the pressure of SO3 divided by the pressure of SO2 times the pressure of oxygen. Now everything is raised to the stoichiometric coefficients, which means that oxygen is to the power of 1/2. And this happens to be equal to Kp. P is everything is a gas, everything is reported in pressure units, is Kp. I'm actually going to skip the second one, and I'm going to do the third one. The third one is that of H2CO3. Oops. Aqueous solution is in equilibrium with water as a liquid plus CO2 as a gas. Here, the equilibrium constant is given by pressure of CO2, because it's a gas, times the concentration of water divided by the concentration of hydrogen carbonate, carbonic acid, because it's an aqueous solution. One other thing to point out is that this looks a little bit weird. I'm guessing you can see that. Solids and liquids have unit activity. So their activity is equal to 1, to unity. What that means is that this equilibrium constant K simplifies to the pressure of CO2 divided by the concentration of carbonic acid. All right, that's the first and third one done. Just going to go back to does anyone have any questions on that? Then I'm going to go back to this list and ask that you work on the remaining 3, numbers 2, 4, and 5. And I am going to put people into breakout rooms and give you about 2 minutes to work on these. So work on 2, 4, and 5, and be prepared to share your answers, please. Get a few more breakout rooms. So you have about 2 minutes. I don't know if you can hear me still, but I'll call you back in about 2 minutes. By the time you get to the breakout room, you should have an answer for everybody. There we go.
Roy.
Yep.
When they're in the breakout rooms, they're not able to see the screen, so some people are asking for the reactions.
I don't have the ability to do that. I can't share it. Yeah. All right, so I'm just going to pull everybody out of the breakout rooms, and then we're just going to go from there. So if they need that. Thanks, Shamitha.
No worries.
So I pulled everybody out of the breakout rooms because a number of people were commenting they didn't actually have the reactions. Yes, I know you've been kicked out of the breakout room. A number of people were commenting that no one had the reactions, and so how are they going to do this? So you need to have this stuff printed or available to you more than just electronically. I won't do it again. Have the notes available to you. Still give you about another minute to finish this. Then I'm going to ask people to contribute their responses. Actually, it's been 2 minutes now, so hopefully people have got some. Does anyone want to share their response? What do they get for the equilibrium constant for reaction 2, please? Someone?
So I got the concentration of CH3CO negative times the concentration of ion of hydrogen over the concentration of CH3COH equals KE.
Excellent. And this, because everything is a solute, it is Kc. Good. How about the third one? Someone else? Anyone else?
Hello?
Yep. Yep.
Okay, you're talking about the fourth one, the H2O
Yep.
liquid. Okay, I got the K is equal to the pressure of H2O because the liquid one doesn't, or gets removed.
Liquid one has unit activity, right. The liquid has unit activity, so K is just simply equal to the pressure of H2O, and that also happens to be Kp for that reaction because it's just gaseous. Excellent.
Yeah.
And someone else for the last one. Anyone else for the last one? Someone who's answered already, want to give me the last one, please?
Okay, so I put the pressure of hydrogen times pressure of carbon monoxide over the pressure of carbon times the pressure of water equals Kp.
What is carbon here? What's the state of matter of carbon?
Yeah, call it, I should have asked it.
Right. So it's not needed. It's just the pressure of water. Carbon, being a solid, has unit activity, and so it doesn't need to be included in that expression. Good. All right. How about the relationship between Kp and Kc? I'm not actually going to go through and derive the relationship between Kp and Kc. I'm just going to give it to you. And that is, as presented here, Kp is equal to Kc times RT to the delta N gas. I am going to just take a few seconds to tell you how this comes about. And where it comes from is the ideal gas law. Okay, and so one can put N over V is equal to P over RT, and this is the concentration pressure relationship. concentration pressure relationship. Concentration, pressure. And with that concentration pressure relationship, you get what you see here. Kp is equal to Kc RT to the delta N gas. And I'm going to explain what that means by doing a couple of examples. So the first one we're going to look at is the SO2 reaction. And so we have 2SO2 as a gas plus O2 as a gas is in equilibrium with 2SO3 as a gas. And what we are presented with here is that K at 1000 Kelvin is equal to 3.29 times 1 over bar to the minus 1. We'll look at the units in just a few seconds, but for now I just want to write down the equilibrium constant expression just to tell you where this comes from. For the units, this would be pressure of SO3 squared over pressure of SO2 times pressure of oxygen, and pressure of SO2 is squared as well. So the units that come out of this, excuse me, would simply be bar squared, since I'm using bar here, over bar squared times bar. Bars cancel, and I'm left with 1 over units of bar. You can always figure out what the units are just by going through the equilibrium constant expression and plugging units in. For our purposes, we have to convert this Kp to a Kc value. And so we have the relationship Kp is Kc RT to the delta N gas. We have Kp. That's what was given up over here. Kp is 3.29 times 1 over bar. In order to solve for Kc, I get Kp divided by RT to the delta N gas. Now, just as a reminder for me, let's go back to basic algebra. What is 1 over a to the x? How does that simplify? Anyone? A to the minus x. Good. A to the minus x. So that means this expression can equally be written Kp RT to the negative delta N gas. All right. So now to solve for Kc. And we have value of 3.29 units of 1 over bar. The value of R we need is one that deals with bar and hopefully gives us units of concentration, because we're trying to get to concentration. The value that is of interest is 0.08314 liters atmospheres per mole Kelvin. And the temperature was 1000 Kelvin. Now we need delta N gas. So if I go back up to my equation that we're working with here, delta N gas is the number of moles of gaseous products, 2, minus the number of moles of reactant gases, N is equal to 3 here. There's 3 moles of reactant gases, so delta N gas is equal to 2 minus 3, which is negative 1. So delta N gas was negative 1, and so a negative 1 is simply positive 1. And so the units are positive 1 here, so that doesn't change. Looking at what we've, liters, sorry, that was an error on my part. This is liters bar per mole Kelvin. That's an error, my apologies. Kelvins cancel, bar cancels, and we're left with units of liters per mole. Liters per mole is 1 over concentration, which would make sense as well. So just very quickly, if you were to do this entire thing in concentration, it would also be 1 over the concentration. So we're good. Plug this into a calculator, and you get a value of 273.5 liters per mole. That 5's not significant. I am just carrying an extra digit through my calculations. And that is what Kc is. All right. There is one more to do, and that one is for you to do for next class. So your task for next class is to go through and do that second example and come back and determine Kp for that system. Does anyone have any questions? Well, you know, Benjamin, just on a humorous point, punctuation really matters in terms of your comment, but I think what you're trying to say is that it makes sense to you. I hope it makes sense to you, but we'll go with that. All right, well, if there are no imminent questions, I'm just going to stop the recording, and I'm going to hang around for a little bit and answer any questions that do come up in whatever you want. So everyone, I will see everybody on Friday. Take care.